Sorry, guys. It's my fault right now. I'm kind of starting late. I'm sorry.
No, we're okay with that.
Oh, sad thought.
It's also Wednesday, which means there's
Oh, true. Fun things. Fun things. I apologize multiple times. There we go. Okay. Okay, thank you guys. Thank you for your patience, and please listen to me. I want to remind you, Michael wanted me to share this information with you. He is, on Mondays from 4 to 5:15, he reviews. You can stand up. Michael over there. Can you guys look at him quick? And you know what? I'm buying you chocolate if you guys can keep your mouth chewing. I'm sorry, that was very mean. I don't know where it came from. But Wednesday also 5:30 to 6:45. No, just chewing, not doing anything else. So no, seriously, I'm talking now. I do want to go over this problem because you guys were kind of rushing out when I describe it. Thank you. So what happened last time is that we decided, right, that if f is gradient of f, and I said, how do we check that it's gradient of f? You have to make a nice domain. This is 16.3. I'm not discussing it. You guys, for this one, you believe that I can't find a nice domain, right? And then, or partially nice domain. And then the other thing that you need is, basically, I have to do a subdomain. And then the next thing is you have to make sure gradient of f is 0. That means that f is irrotational. Then, if you stay quiet, I may buy chocolate for you guys. Yes? Okay, I'll do it. Let's see how long we can stay quiet, though. So now, if f is equal to gradient of f, if these two conditions are served, and I'm saying that this is going to be okay, just don't worry about it. I'll find a subdomain for now. Check the curl of f. Curl of f by checking this. I, j, k. Curl of f, curl comes with what? Cross. Divergence comes with dot. And so I will have the nabla, which is just a partial nabla operator. And then y squared plus e to the z, 2xy plus secant squared of y, x e to the z. You guys try this and you end up with a 0 vector. Homework. Now I want to find its potential function. How do I find the potential function? Is that in my mind, I remember if f is equal to gradient of f, that means that f is equal to partial of f with respect to x, partial of f with respect to y, partial of f with respect to z, the three components. Now, what do? I do antiderivative. Antiderivative of this. So the first component, f1 is that, f2 is that, f3 is that. Some of you guys had an extensive work done this morning in your labs. I was kind of behind lab did it first, but they knew that you didn't have the instruction entirely. So now, when I'm taking the antiderivative, to release f, I need an antiderivative with respect to dx. That's y squared plus e to the z dx. Then over here, I need antiderivative with respect to y to release f, 2xy plus secant squared y. And then over here, I need antiderivative with respect to z, and that's what I get. Now, the next step is important. Please pay attention here. When I take the antiderivative with respect to x, what do I get? F of x and y and z equal to, which is the potential. Antiderivative of y squared is y squared times x. E to the z is e to the z times x. I'm going to leave a little bit of space. Now, antiderivative of that is x y squared plus, what's the antiderivative of secant squared of y with respect to y? What trig function's derivative is secant squared? What? Tan of y? Yeah? And then I would have over here the antiderivative of e to the z is e to the z. This has a very problematic piece. What's that? Yeah, that's what I'm saying. There's a problem in here. These are not the same thing, are they? Nick, do you want to go back to your friends? Okay, you're good. You don't like them? You like me better?
Yeah.
Okay, that's good. So what is happening is that, okay, so these two terms, look at these two terms. They're appearing with the first and second antiderivative. Then I'm looking at that one. It doesn't appear in any other ones. Then I'm looking at this one. It only appears in the first and last antiderivative. Why is this problem? Because I didn't include I didn't think about this c. Here, I would have a constant, but constant in terms of x, is y a constant in terms of x? Is z a constant in terms of x? So the constant in here, and I call it C1 because it's different here. It depends on x. This constant depends on x. So I have y and z. Then I will have in here depends on y. So I have x and z. Then it depends on z. Therefore, I will have x and y. So now carefully check. What could be your constant, the function part of it, not the constant part of it, right? So I'm looking at this, and what are the function of y and z in the other two? Y and z only. I have that. So this can be part of it. Also, this one is x e to the z. It's not part of it. And that one has x. Therefore, this C1 must have tan y, must be tan y plus a constant c. Fair game? Because it appeared in other places. And it was just I don't know what this function of y and z is. So it's obvious it wasn't Nick's problem. He basically exonerated his name. So now the next thing is this. Now you could do this for all of the other ones, right? I can go see 2 of x and z. Where are the functions of x and z only? Only this one. So C2 of x and z, e to the z plus c, and so on and so forth, and find every constant in there. But then pay attention to this. When I found this constant, what did I get? I get f of x and y and z is equal to x y squared plus x e to the z plus tan of y plus c. Agreed? If I do it with this one, I also get the same stuff. And if I do it with the last one, I also get the same stuff. So you just need to find a constant in one of them if you need to. Sometimes it's not easy. Sometimes you need to do a little bit more work. And I have a video in this course. We're not doing the way that is difficult to do. That is a course in differential equation, one higher than the one that you're taking. That would require harder ones. We're doing the basics in this course, and that's what we're doing. So remind me, when I do, let me think about this again. If all my questions are going to be the simplest ones, what did I do? I looked at the things that are repeating. I wrote them down once. So y2x and xy2 are the same thing and repeating, it's not just once. I wrote it once. Wrote it how many times? Once. I looked at x e to the z, it was repeating. I didn't write it twice, I wrote it once. Then I looked at, see if any other terms are there. That one is just once, and I wrote that one once. So I added them all up, and that becomes my potential function. Potential functions are very important because it really gives you the potential energy eventually. So we talk about it in 16.3 again. But before 16.3, we wanted to talk about it. So now that said, this is going to appear on your, what is that thing that you do in the lab? Worksheet. And maybe quiz, no. Too early for quiz. So what is happening here? You guys are going to be given a potential function. Can you see this potential function? If I give you a potential function, can you give me a gradient field? What is the gradient field of this? Gradient of f, oh, sorry, it's not f. Who said f? R. Gradient of r is going to be partial of r with respect to x, partial of r with respect to y, partial of r with respect to z. So you compute that, and you get a gradient field. This gradient field has a lot of nice properties, and so you explore it in the lab. Fair game? And it's actually very useful for physics and engineering. It's radially, repeat after me, radially outward gradient field. That's the one. When you do it, it looks like that. Do you see the arrows are going outward? It's the unit radially outward vector field. Unit, because it ends up, except it's not defined at origin, but everywhere else. But do you guys know why it's not defined at origin? It turns out that the vector field at origin is zero vector. Nick?
On the worksheet for the it was asking us to define a curl and divergence or something like this. I don't know how would you go about that?
Oh, you just, so you find the gradient field first, and then it's a gradient field. So it's gradient of f. What is curl of gradient of f? I want you to memorize this, or I always had it in your head. Gradient fields are curl-free. So curl of gradient of f, that's the one that you guys are proving a bunch of times. Curl is going to be zero if it's a gradient field. And then divergence is just take the derivative of each item. Gradient fields are divergence-free. Gradient fields are curl-free. I said it wrong. And then divergence of curl is zero. We tell you something else later. It's not always scalar potential. Sometimes you have vector potential. May I? Ta-da! No? What, did I miss iClicker? No, iClicker is going to come soon. So now we're going to talk about 16.2, and I had this beautiful picture. Imagine top of this is a curve in space. Can you see the top of this? It's a curve in space. Do you see how curvy and pretty it is? Let me show you over here. Curvy and pretty. have to be old and fat for that. And I'm like, that would be me. So, you guys cannot do that. Body shame yourself. I am there for you. So now I have this curve. Do you guys remember in CAC 1? What did I do in CAC 1 with this picture? Can you see it in the back? In the back. Riemann sum to find what? Area of the curve. Oh, what about if my curve is curvy? So now it's like what we do is called, look at the name, line integral. Because line in this space, it's a curvy line in this space. And I still want to find this area underneath this, even though it's like that. So literally, what we're doing, the process that we're doing is undoing it into a flat land and computing it. We would bring that back into the integral in CAC 1. That's what we do. Compute it so it would be an integral in CAC 1. What do you mean 3-figure? 3 pieces? If there are 3 pieces, yes, it will be. Exactly. But this one is kind of smooth. It's 1 piece. Ready? Let's go. So what we do next is, let me show you. So again, it doesn't look like it in the beginning, but look at this. Do you see the curve on top? Okay. Do you see there is a red curve? I don't know if everybody can see. The red curve on the bottom. Everybody can see that? So what is happening is that red curve on the bottom is going to be my domain. It's going to be my equivalent to my x-axis. And one thing I want to say, if the blue curve on top goes under the xy plane, it's like CAC 1. Area above minus area below, right? Area above minus area below. And what else do I want to say? So I want to do a Riemann sum again, right? You guys are all for a Riemann sum. So that's how I do the Riemann sum. I'll take a little piece of that curve. So I compute a little piece of that curve in the domain, in the bottom part, where all the bases of these rectangles are sitting. Little piece of curve. And then I find a sample point on that little piece of curve, and then I build a rectangle on top of that. And then I approximate, and I make the rectangle smaller and smaller, and we go on. This note says, basically, if you have a curvy shape, without the y, it would be exactly CAC 1. Integral, so you don't have to even worry about that. But what if it's not, and then we discuss it. Let me bring you up to this. Let me put that over here. I may be trying to convince you too hard. So that's a picture. That's a curvy curve. You can see the pink curve on the xy plane. And then the little pieces are getting smaller and smaller. And then the area gets closer and closer to the Riemann sum. Oh, that's for the next part. How do I get rid of this? There we go. So again, let me write down the Riemann sum. When I talk about curve in this space, right, what do I think about when I say curve in this space, or where did you guys see curve in this space in this course so far? Curve in this space, what chapter it started? It started with 13, so and so in chapter 13 you saw it first, and it came with a parameterization. And so you have a parameterization that comes with the curve. this section is only using that parameterization to take a curve in 3D into a curve in 2D, right? That flattening the curve that I did is using a parameterization. Fair game? Okay. So look at this domain. What I'm going to do is I'm going to break this into multiple pieces, right? Multiple pieces right here, and many pieces. Then I'm going to choose a P1, P2 in each piece. In each piece, I'm going to choose a P. That is my sample points. Then I would place that. Where did my curve go? Then when I'm placing this curve on top of it, can you guys see this? Yeah. Okay. Then I know the height of each rectangle by plugging in those points into the function of this curve. Okay, z value of that curve, basically. So what you get is this. Basically, you get f of pi. You multiply it by the arc length right there. So what was the arc length? Arc length was r prime of t magnitude delta t, right? So the height times the arc length. Little arc length. And then this is the height with the sample point. Then you sum it up. Sum it up. And then you take a limit. And this gives you the integral f of x and y ds, which is that area that we discussed, and that's the notation. Fair game so far? Okay. Now, you guys are waiting for an example, huh? No. Not yet? No, I think it's right after this, right? Right. I think so. So integral of f of x and y s over c, which is a curve, is going to be the f of r of t. Then, I forgot something. What did I forget? ds. This is notation. According to that Riemann sum, it's going to be f of r of t, magnitude of r prime of t, dt from a to b. That's the notation. It tells you you're multiplying the height by the small arc length, basically. And that's what you get. One thing I want to mention, this is, again, called arc length element. Do you remember you had area elements, you had volume elements, now you have arc length element. And example time. Okay, so what is the formula, my friends? What was the formula? And I'm going to extend this to 3D also, right? But let's see. What is the formula? FDS is equal to f of r of t times what? Magnitude of r prime of t dt from a to b in 2D. I mean, when the domain is in 2D. Now, the same thing is for 3D. It doesn't matter. I just explained the pieces in 2D, right? But then 3D is the same. Anybody has a question about this so far? No? Remember, if we're staying quiet, I eventually buy you chocolate. This one is R prime. R prime, very good question. R prime, magnitude of R prime. Why? Because this is what is this called? Arc length element. Because I want to multiply the height by arc length to get the Riemann sum done. Each piece of Riemann sum. Now I'm starting, oh, what is my F? What's that? F of x and y is 2 plus x squared y. That's exactly the same notation. If I want to compute this, I have to have a parameterization. Can you guys give me a parameterization? So use the trig functions. R of t equal to cosine t and sine t. T goes, is it a full circle? That's done. What's the next? I needed a parameterization to find arc length. So how do I find arc length? Take the derivative. R prime of t is negative sine of t and cosine of t. Agreed? Now, what do I need to do to arc length? I have to take the magnitude of this. Magnitude of R prime of t is square root of negative sine of t to power 2 plus cosine t to power 2, which is 1. So my arc length element is 1 times dt. Now let's set up one more step. What is f of R of t? My friends, how do I compute f of R of t? It means if R of t is x of t and y of t, cosine of t and sine of t, f of R of t means f of x of t and y of t. So I plug in for x, I plug in the parameterization of x. For y, I plug in the parameterization of y. So f of R of t is going to be, what was f? 2 plus cosine squared t, sine of t. Everybody okay so far? Can I set up the integral? Integral, oh, what are a and b? 0 and 2 pi. And I have 2 plus cosine squared t, sine t. Then I have 1 dt. Do we know how to integrate this? So I integrate 0 to 2 pi of 2 dt plus integrate 0 to 2 pi. Can anybody quickly tell me what is the second integral? From 0 to 2 pi, what would this be? It would be 0. Can you guys do the second integral without computation, by the symmetries? Because sine of t is an odd function, right? All the values as I'm going around the circle, all the values that I take above the circle, I get the negative of that below the circle, because sine is an odd function, or, right? So they actually cancel out. But if you are doubting yourself, do the U substitution. Did that make sense, the symmetry? Who has a question about the symmetry that makes this 0? Because when I'm going between, look, between 0 to 2 pi, for sine of t, cosine of t is positive about here, right? The picture is not very good. Somewhere positive. And then it becomes negative because sine of t is negative. If that makes sense. And so they add up to be the 0. The picture is not good, but the positive above the 0 to pi, and the interval 0 pi parentheses, and then pi to 2 pi parentheses, quantity in parentheses. So those two interval, and so they cancel each other out. Did that make sense? Should I do the U substitution or not? No, we're good? Plus 0. Okay. This is a very good, I'm trying to get you prepared. I do another U substitution, but I'm trying to get you prepared because some courses require you to answer this quickly. Make sense? Because cosine of squared is always positive. Sine of t, the sine of the graph goes with sine of t, and they're very much, they are very, what is that called? Symmetric. Ready for the next question? Hold on. Do you want to do one? Yes. Let's do one. I think you guys are getting antsy at this point. Rightfully so. Rightfully so. So compute this. He cleared his name for sure. So, my friends, do you need to do the step 1 I did over there? No, it's already given. You're good. Step 1 is given for you. So take the derivative. Doing good? Yeah. Why do you take the derivative of r? You're trying to find the arc length element, yes. Mm-hmm. So who knows what the magnitude of the r prime of t is? No, you were right first. So if I take the derivative, I get negative sine t, cosine t, and 1. And so sine squared plus cosine squared plus 1 is square root of 2. Yeah, because it's magnitude, right? Magnitude has a root in it. Now, what do I plug in into the integral? My friends, what is the integral? What is function f? You plug in cosine t, sine t, and t in here. What? Cosine squared t plus sine squared t plus t is 1 plus t. Right? 1 plus t. You guys are okay? Are we doing okay here? Any questions? Did everybody get magnitude of r prime of t equal to square root of 2? Everybody has that? Then you have the function, which is, what is the function if I plug in the parameterization? Is t plus 1. Now, I can take the square root of 2 out and take the integral from what to what of 1 plus t. 0 to pi. Uh-huh. Good.
So I was telling him this, right?
Let me go compute. I don't remember. Well, integral of 1 is pi times square root of 2. Integral of t is t squared divided by 2. Yes? Mm-hmm. Doing okay? At least do the work on the board. Okay, so did everybody get everything done? Unanimously. Yeah. Mm-hmm. Square root of sine squared t plus cosine squared t plus 1.
Why is that not sine squared t and cosine squared t not equal?
Yeah, this part equals to 1. That's why I get 2. So 1 plus 1. That's okay. It's a lot of pressure. Zero to pi. And apparently somebody gave you the answer. 4, 3, 2, 1, 0. Okay, so now I'm going back to this. I promise you chocolate, if you guys are good kids. Candy? Okay. So the next thing that I want to say, what if I have multiple pieces? So multiple curves. I have to divide them up, compute value on each, add it all up. Summation, exactly. So now let's read this one. It tells me that there is a piecewise smooth curve consisted. Piecewise smooth means each one of them has a so I have C1 that is a piece on parabola from 0, 0 to 1, 1. And then I have C2 that is a line segment from 1, 1 to 1, 2. Should we draw this? Time to draw. XY plane. This is point 1, 1. Then from 1, 1, it goes to 2, 2, 2, 1, 2. C1 and C2. So first of all, I'm going to draw a line, compute the integral over C1, and then compute the line integral over C2. I'm sorry, that C1 is too high. On the curve C1, and then on the curve C2. What are the steps? Step 1 is parameterize this one. How do I parameterize a curve y equal to x squared? Y equal to x squared? It should, to pull what? No, should to So now I have step 1, parameterization R1. Because, wait, can I use x as a parameter? Sure. What would y be then? If x is parameter, what would y be? T squared? Sure? I'm parameterizing y equal to x squared. That's a valid parameterization. Not everything has to be trigonometric. Yes, ask Avery. You good? Step 2. What is R1 prime of t? What is the magnitude of R prime t? Do you guys agree? Agreed? Now, what you need to do, step 3, compute f of R1t. What is f? So when I plug in, it's kind of early for physics. 2x, right? 2x. So I plug in 2 times, what is x here? So this integral is going to be from, and where was t here? Bound for t. It starts at point 0, goes to 1 and 1. So maximum t is 0 to 1, 2t, square root of 1 plus 4t squared dt. That's the setup of the first piece. Second piece. How do I parameterize a line? How do you do parameterization of a line? I could do that. Hold on. Let me show you this. So I'm trying to do R2t. I do like to. What you said. Can you guys pay attention to this? It's once for all. We just had a suggestion. The suggestion was that to do 1 and t. So what is t in here then? So what is the min and max? 1 and 2. Right? So it's not 0 and 1 anymore. There is another parameterization that I can do, and t would be between 0 and 1. Anybody knows that? No? What is the other parameterization I can do? I can start from beginning point 1 and 1. Beginning point 1 and 1, then add t times the vector. What is the vector between 1 and 1 and 1 and 2? 0, 1. This parameterization, I'm going to get rid of that one because I want to focus on this a little bit. That one is very valid, but I want to focus on this. So I get 1 plus and 1 plus t. In this case, the parameterization t is between 0 and 1. Now, this is step 1. Step 2 is computing R2 prime of t, which is square root of 1. Agreed? So it's 1. Step 3 is computing. Did I do a mistake? No. I didn't compute R prime. You're right. I computed our magnitude of R prime. 0 and 1, R prime of t is equal to 1. Step 3, f of R2 of t. I have to plug in, what's the parameterization? 1 and 1 plus t. I have to plug in x, I have to plug in 1. So it's 2. So this is going to be integral from 0 to 1, 2 times 1 dt. Fair game? 2 pieces. Now I'm going to add it. Do you guys want me to compute the integral? No? You can do it on your own? Should I tell you what u substitution it is? Okay. So the integral, watch me in this, integral f over c ds is equal to integral f ds on c1 plus f ds on the c2. First one turned out to be 0, 2t square root of 1 plus 4t squared dt. The second one, integral from 0 to 2, 2 dt. Now I'm going to do, take care, guys. Good luck with your quiz.
Thank you.
So now what do I have? This one is easy to compute. That's just 2. Here, what I need is to have a u substitution, 1 plus 4t squared. Then du is going to be what? 8t dt. Oh, I do have a t in here, right? So I can set this up as, oh wait, if t is equal to 0, what is u? Plug in 0, 1. If t is equal to 1, what is u? 5. So it's going to be integral 1 to 5. And 8t dt is t dt is equal to 1/8 of du. So t dt is 1/8 of du. So 2 times 1/8 of du times square root of u. Agreed? Plus 2. And then I'll let you do the rest of the integral. No? Okay. So it's integral of 1/4 of u to power 1/2, 1 to 5 du plus 2, which is u to power 3/2 times 2/3, which is 1/6 of that. 1 to 5 plus 2, that is 1/6 of 5 to power 3/2 minus 1/6 of 1 to power 3/2 plus 2. And then you compute it. Good? Okay. And you common denominator and stuff, which I'm not doing. This one we did. And I have about 5 minutes that I want to talk through some theory on what the other integral is. So far, what have I computed? So far, I have computed scalar line integral. Scalar line integral comes with a scalar function. So what we did here, we had an f that was giving us a number, right? It wasn't giving us a vector. F was giving you a number, not a vector. And this scalar line integral basically computed the area. Now I'm going to do something wonderful that you wanted to do in Calc 2, but you couldn't. I'm going to do a vector line integral. Vector line integral is when you give me a vector field, then I give you basically an integral of how that vector field is acting on a path. So someone throw me a rope. I'm going to honor this curve. Somebody throw me a rope. Start pulling me. Play around, play around. Someone. Okay, thank you. Pull me. So he is the vector field. And the components of his force field on the path that I'm going, right? I have to take that vector field, put it in the direction I'm going. That's the vector field, but I want to know how it's acting, the components on my trajectory. So he's pulling, I'm moving, but not everything that he's pulling is on my path. Some of it is otherwise. So I have to find that. And then I have to multiply by little ds that I'm moving to find the little work done